the user is in distress, they can automatically activate that mode. The ADT is simply going to be an ITBD with an added daughter card on it that has the external hardware that allows for it to interface with the radio for longer range communication. By having just a card, any ITBD in the field at any time will be able to attach this card and essentially become that long transmission source. The ground station is going to receive all these messages that are sent from the ADT and then display them on a graphical user interface, so the user will be able to see the relative locations of all the users in the field to each other and their vitals all in real time. So overall, the system is going to be made up of a maximum of 48 modules. There's going to be 3 ADTs and 15 ITBDs per ADT. Keep in mind though, each ADT is also an ITBD, so it'll collect data from itself, which is where the extra 3 come, or 48. For one system, there must be at least 1 ground station and 1 ADT. This is the minimum location out in the field from one user and be reported back to the ground. We can go over this 48 limit, however, according to our spec we designed, we want to be able to contact every single device in the field at no more than 1 minute intervals. If everyone was in emergency mode, 48, we have a very slow baud rate of only 1200 baud for the longer range UHF, VHF communication, and that set our limit at 48. So here's a more expanded diagram. You can see the ADT right here is going to create its own local Wi-Fi network that it will host, and all ITBDs will be routers in that network. So each circle will be a closed network up to a quarter-mile radius where all the data will be gathered from the ADT from the ITBDs. Then the information will be transmitted via UHF VHF radio to the ground station. The UHF VHF packet will not be an aggregated packet of all the ITBDs. It'll just be one. So when the ground station sends a request, it'll get data from one ITBD and send that information back. I'm going to pass it off to Tim to talk about our process.
Thank you, Aaron. So starting off with our strengths, this was the computer engineering, electrical engineering prelim and detail capstone project. This allowed us, with the vague client request, allowed us to engineer the solution in a way that would benefit us. We have 4 computer engineers and 1 electrical engineer. This allows us to make the device more towards our strengths instead of our weaknesses. We will not have any mechanical parts. This is not an avionics related piece. This allows us to be very strong in our programming and to have also the benefit of electrical components being thoroughly looked at. We also had experience in the past with XB radios, which allowed us to get a jump start on the XB radios, but we still had a lot to learn about them. We also have had classes with microprocessors that gave us a jump start, but there's still a strong learning curve there. And we took real time, which allowed us to implement sensors and how to most effectively meet deadlines in very low time. We also had access to a rapid PCB mill, which allowed us to make multiple copies of our PCB on the site. Weaknesses. Again, we had a vague request that makes it very difficult. We have to spend extra time to come up with a solution instead of doing the busy bee, hand the papers down, and go at it. GUI experience. The classes are now being offered at Embry-Riddle as of next year. This did not allow us to have any experience in GUIs, so there was a very strong learning curve there. And we had no prior experience in ham digital packet transmissions. As this was our backbone for our project, this was a very large weakness that we encountered. Opportunities. By doing this project, we were allowed to give back to the community instead of doing a corporate-sponsored product or a personal product. This allows us to interact with the community that usually is offset among Prescott people. Sorry, lack of better terms there. And the college students that usually don't get along. This allows us to create a bond that hopefully will make a better community. Also, this is a field that doesn't have a lot of technology already incorporated and allows us to help them do their job better and more effectively. And this final capstone project allows us to learn knowledge that we would like to learn before we leave the college. I'll now pass this off to Becky.
Hey, so I'll be going over a detailed hardware analysis of the ITVD, which is the device that collects information from each individual. Just to recap, ITVD needs to be able to collect heart rate, location, and ambient temperature data. It must be able to monitor the emergency and power switches, and it must be able to monitor battery. And, another thing is that we're programming it to go into emergency mode if the heart rate is below 30 and above 200, because these are levels which are considered dangerous levels, and it will switch the device into emergency mode at that time. All right, so here is our block diagram of the sensors that are connected to the ITVD. Here we have a microprocessor. We're using the CAM-M8Q GPS receiver, and this communicates with the board using SPI. We also have 3 LEDs here. One of them is for emergency mode, so if it's flipped to emergency mode, it will turn on. The power LED to say whether it's on. The ADT lock LED, this says whether it's transmitting to the ADT. That's the relay, the ADT. This device uses ADC for temperature sensing and battery monitoring. Here we have an emergency mode switch that is connected just straight to a GPIO pin. We have a Bluetooth receiver. This Bluetooth receiver collects data from a heart rate watch that we'll talk about later. This Bluetooth receiver communicates with the microprocessor using expert C. All this data is collected and sent to the ADT relay using XP radios. The XP radio receiver communicates with the microcontroller using UART protocol. Right. So we picked up the MSP 430 because of its low power consumption. 290 microamps per megahertz at 8 megahertz. This is a GPS we picked, mainly because of its high sensitivity. It interfaces with the microcontroller using SPI, since we had a low number of UARTs. The reason why we picked this heart rate watch is because it's one of the few on the market that actually collects heart rate during high activity. The Bluetooth receiver communicates with the microcontroller using I2C. Ambient temperature we chose collects or sends data using 12-bit ADC to the MSP 430. And this is the switch we use for the power switch and the emergency mode switch. The power switch is connected straight to the power supply, so it can tell whether it's on or not. Emergency mode switch, like I said before, is just connected to a GPIO pin, as I'll show later. And XP is how we're transmitting the data to the ADT relay. The ITVD XPs are configured as AT routers. So here's a schematic. Here we have the temperature sensor. Here we have the XP Pro, which sends the data. This here is the GPS. Here's the connections to the LED switchboard. So what we're going to do is there's going to be an this is the main ITVD board, and then there's going to be the power and the power board, and then there's the switch and LED boards, which we're going to be going over. So this is just the main ITVD board. That's why we have connections to the switchboard. Here's the connections to the GPS. Here's the connections to the Bluetooth receiver, and here's the connections to the these are the connections to the MSP430. Here's the ITVD PCB. I'm going to be passing around what we currently have as our PCB layout while I talk about this. Alright, so when I'm passing it around, please don't touch any of the components because we're worried about static, but just handle it from the outside.
Maybe you can put it on that mouse pad and pass it around on that blue mouse pad.
As you can see, the MSP430 is put on the bottom of the ITVD board, but as you can see, we have the connectors to the XP here. The GPS is connected here. Switchboard connections. Since the power supply is on a different board, we have the connections for the 3.3 volts and the 5 volts connected here. The MSP430, as you'll see, is we got these pins, and these are all just connections to MSP430. These are the connections to the Bluetooth receiver, and this is the temperature sensor. Currently, our PCB board that we're passing around is not completely tested yet. Then we can lack time. We do have a complete mock-up that is working, which I will show after the switchboard, with a complete 3 different boards connected to it. This is the switchboard that's connected to the ITVD. Here we have the ADT lock and the emergency LED. Here we have the emergency switch. The emergency switch is connected to a GPIO pin on the MSP430. The power switch is physically connected to the switchboard. However, it's electronically connected to the power board, which we will see which Dave will talk about later. Here's the PCB layout of the switchboard. I'll be passing around, this is the power board connected to the switchboard. This one has been tested. ITVD board is not quite functional. Here is the current mock-up that is currently tested, and we tested it yesterday with Dr. Davis, and it works, the GPS works. We'll go over what exactly is working right now, but this is the current mock-up that's been tested. Here we got what I've been passing around the power supply. We've got the switchboard and the ITVD connected with the XP. So here to go over where we're at and what's functioning on the mock-up and what's partially functioning. So in the mock-up, the GPS receiver works, ambient temperature works, battery level, data transmission to the ADT works. We tested that. And the power and emergency switchboard is also tested and it works. What's partially functioning is the PCBs. The main ITVD PCB is not quite functioning yet. And the heart rate receiver, Bluetooth receiver is not receiving heart rate. So I'm going to be turning it over to David to talk about the ADT.
All right, thank you. So now I'm going to discuss the ADT. So this is the device that collects all the information from the ITVD and then packages it and sends it back to the ground station. So this is essentially a relay. So the block diagram for an ADT is essentially almost the same as an ITVD, but with the exception that we have an MSP or MX614 connected here, which connects to a radio, and we have a display connected up here. So the communication between the ADT and the ITVD is going to be over those XP radios. The XPs for the ITVD are going to be configured as AT routers, and the XPs for the ADT are going to be configured as API coordinators. This radio communication is short range, line of sight, so this is that circle of devices in that, around the ADT. So the communication between the ADT and the ITBD, or and the ground station, is going to be utilizing a MX614. This is to modulate and demodulate transmissions, so we can utilize UHF and VHF communication. This allows us to have a further range regarding if they have transponders out in the field, then we can get further communication. So it depends on what network the people that are going to be using this for the radios have for the distance that this system travels. So here we have a picture of an MX614 here up top that is receiving bits. It is modulating that bits into tones and then sending it out to another MX614, which that MX614 is demodulating it back into digital signals. So you can see there's a little delay here. And here's what those tones look like. You can see that we have a logical 0 and a logical 1 here. The 1 is a 1200 hertz tone, and the 0 is a 2200 hertz tone. So for the hardware on the ADT, it's going to be utilizing this MX614 right here, which I just want to note that with our energy detect pins and our receive and transmit pins, and we have our audio jacks to connect to an interface with the radio. So also on the ADT is going to be a display. We chose an Adafruit OLED because of its low current draw and its configuration through SVI. So here's an overall schematic of the ADT shield. If Bob would like to pass around the ADT. We have our MX614 up here, our connections to the OLED. We have our connections to the MSP430, which is on the bottom again. It actually is a shield, so this device, the ADT, will go right on top of what we passed around that ITBD. So it's, each ADT is essentially an ITBD as well. And then we can also see that we have a XB right here. So here's more better description about that PCB. As you can see, we have the XB up here, our connections to the MSP430, our MX614, which I'm sorry you're not going to be able to see because there is a display sitting on top of it. And then we have our line in and line out for connection to our radios. So here's a picture which hopefully should match that one that is being sent around. So our status of the ADT, we have transmissions of data requests from the ITBD working, and we have data receiving from the ITBD. So that's kind of what we have working. What is partially functional, we are having some problems with the AX25 data packets. That's the radio signals and the display. And the ADT shield itself is, there might be some power issues with it right now, but it's too certain to tell exactly what the problem is. So now I'm going to discuss the ground station dongle. So the ground station dongle is that other side of that ADT which connects to the ground station. So it's going to be receiving those communications and modulating them back for the ground station to use. It is going to be connected to a computer, and it is what transmits and sends data from the ground station to the ADTs. So we're going to be using a USB connection for that ground station, so it's going to be powered off of that. And it's just connected over USB to a computer. So for the block diagram for a ground station, we essentially just have a USB, an MSP430, and just that MX614, which is also connected to a radio. So the schematic for the ground station dongle is very similar to an ADT that we have an MX614 up here, configured in the same way as an ADT, and we have our MSP430 connected ends. So here's a picture of the ground station dongle. Here, this gives you a better picture of what lies underneath that OLED right here. It's the same circuit, which is the MX614, and here are the lineouts to connect to the radio. So here's another picture of that device, which we are being shown around today. So the status of the ground station dongle, we have transmission from the ground station to the GUI, so it connects to the COM ports on the computer, and the data receiving from the GUI. So essentially this board is working. Like we said, what is partially functional is the AX25 packets. So now I'm going to hand it over to Bob to discuss ITBD software.
That's good. We're just going to try to walk through how the software works in this whole system. So the ITBD, again, is kind of like a big sensor for our system. So it's going to need to grab the GPS location, the heart rate, and the temperature on request and send it back to the ADT relay. From now on, the first thing the ITBD needs to do is link to an ADT. So it's going to sit in this loop and wait for a command to link to a local ADT over in the AXP ranges. Once it gets the command, it's going to do one check and then two checks. This is to make sure that it's a strong signal and that it's actually part of the system. It didn't get a corrupted packet somewhere or a mixed address. Assuming this goes well, it's going to send a command back to the ADT, letting it know that it thinks it's linked, and it's going to light an LED on the ITBD to let the user know that it's linked. From there, it's going to go on to the normal operation. First thing it's going to do is go into low power mode. Low power mode 3 is the lowest we can go and still use the clock signals we need to. From there, it's going to spend most of its life, and it's going to wait for a command, a data command from the ADT. Once it gets a data command, we'll go into active mode, which turns on all the power consuming stuff. And we're going to pull all these sensors in parallel. The temperature and the battery voltage are both ADC versions. The GPIO pin is just the toggle switch if the user decides he's in emergency mode. These two are the slowest sensors to grab, the heart rate and the GPS receiver. We have to communicate with the heart rate over Bluetooth and GPS over SPI. It's going to wait down here once all the sensors come in. Once all the sensors come in, we're going to check for extraneous results like heart rate over 200 or below 30. So the guy's obviously not doing well, and that'll flag the emergency bit. We're going to parse the GPS and the heart rate packet because we don't want to send how many satellites are up in the sky. We just want to send the location. Package that all up and send it out to the ADT. So the ADT, once again, it's the relay in the middle. And this is the same process that the ITBD went through to link on the other side. So it's going to send out a command to the ITBD, and it's going to do the same double handshake check to make sure we can link an ITBD into the system. If it doesn't respond, or if it only half responds, it's assumed to be a weak signal and it'll be disregarded for now. And once an ITBD is linked, it's going to come back and check again for more ITBDs. And once all the ITBDs up to 15 per ADT are in the system, it's going to continue on with the rest of the program. So, at this point, the ITVs are linked. It's going to wait for a command from the dongle. That's right off the ground station. So when this message is pulled, it has to decode the AX25 packet. It's coming in off the long-range radio. It's going to determine if the packet is for the ITVD or for the ADT. If you remember, the ADT is a daughter card. It's physically connected to the ITVD. So if it's for that ITVD, it doesn't need to send out a message to get the one that's attached. So it's going to make, if it is that one, it's just going to grab that data and send it right back over the MX614 radio there. If it needs to transmit to a different ITVD, it's going to construct an XP packet and send it out. From there, it has to wait for the ITVD to reply to the ADT. If it times out, we'll just disregard the packet, let's try again later. Assuming it goes well, we get the packet, we have to decode it, and then reconstruct the AX25 packet to send it back to the ground station. Back to the ground station is where the dongle will receive it. So these two guys here are going to be running concurrently. This whole device spends its life waiting on commands. It's either going to be waiting for a command from the ground station, in which case it'll convert the packet to AX25 and send it to the ADT, which will be relayed to the ITVD, or it will receive a packet coming from the ADT and relay it to the ground station. David's going to talk about the power of the system.
Right, thank you, Bob. So, as stated before, this system is going to be powered using AA batteries. This is because the firefighters out in the field, this is what they have. So for them to have charging devices is actually kind of cumbersome because they don't have time to sit there and have it charged where they can just replace the AA batteries. And the ground station dongle is going to be powered through that USB port. So the power supply here, we have linear regulators, a 5-volt regulator and a 3.3 volt regulator. So here's a schematic of that power board, which is also that switchboard that we have hashed around. As you can see, here are our 2 regulators, and we have a fuse for protection from current. And like I said, here's another picture of that power supply. So we did an estimate of current draw with this device being able to operate in low power modes. So if we were able to operate in a low power mode, we can get the 5-volt devices down to 1.5 milliamps. And if we were able to operate using duty cycles to get our 3.3 volt devices down to 61. But our max current draw for the 5-volt devices is 11 milliamps and 275 milliamps for the 3.3 volt devices. What our average current draw using that assumption of low power mode would be 62 milliamps. But what currently we are testing is 115 milliamps. So this is not in full power saving mode, but yet at least it's not reaching those high levels of the max current draws that we expected. So that gives us an approximate operation hours of, for the ITVDs, around 20 hours. So for the ADT, the 5-volt devices is the same, but we've added 2 3.3 volt devices, so the average current draw is a little bit higher if we are running in low power mode, and our max is a little bit higher if we're running at full max estimate. However, we tested this to be at around 149 milliamps. So that gives us another approximate hours of operation of 16, which is a little less than we really wanted, but still meets our spec of 12 hours. So now I'm going to hand it off to Aaron to discuss system operation and complaints. David. So I'll be going a basic overview of an example of a command being sent from the ground station, and the communications all the way down to the outmost leaf, the ITVD, coming all the way back to the ground station where the data will be displayed. So you see this diagram we have here, starting with the ground station, we're going to go down all the different communication protocols, the different devices, and then the information will be relayed all the way back. So starting with the ground station. The ground station is the master to the overall system. Because everything relies so heavily on radio communications, we have to have one device that's in control of everything, so there's not two devices talking at the same time. The ground station will be the main workload for the system in computing all the times when devices need to be pulled further data to meet spec. This is every 4 minutes for normal mode and every minute for emergency mode. So the ground station is going to issue a command that will be sent to the dongle over UART, and the command will have this following form. Key information here, we're going to have the ADT address, the ITBD address, and then the command that needs to be sent. This command will be received by the ground station dongle, and it's going to be needed converted to the AX25 specification. As you can see, the specification is outlined here. Once the ground station dongle formulates that command, it will send it in this format right here. The key thing here is in order to comply with the AX25 specification, we need the address here of the source and the destination of where the device is sent. Keep in mind the final destination for the device is the ITBD, so we have to move that address down to the information frame right here, keeping just the ground station as the source address and the ADT as the destination address for the address frame for AX25. Once the ADT receives this packet, it is going to need to convert that AX25 packet into an XP API packet. XP packet definition can be seen right here. So once that command is actually sent, it'll have this following format, where now the main part of this device is just the ITBD. So all the address links in here are to get that message to the ITBD, and again you can see the command that the ITBD will be receiving. So once the ITBD gets the command, it's going to essentially wake the device up out of sleep mode and need to gather all the sensor data at that time. Once it has all the data gathered from the sensors, it's going to compute its own checksum. The importance of this is we want a separate checksum for the data section versus the checksum for the entire packet. Because this packet's being relayed through so many different protocols to get back to its final destination, the ground station in the end is only going to receive this frame 7 right here, so it'll be much more efficient to just check that checksum, which will not change as the protocols change. So once the ADT receives that XP message, it's going to need to convert it back into AX25, which have the following form right here, and back we have now the target ITB that was initially communicated as the first data field in the information frame, and then the ADT is now the source, and the ground station will be the destination for this message. And again, we have the separate checksum here that is for just the data that was collected. So once the ground station dongle receives this message, it's going to take the AX25 and strip off all the frames except for that information frame. The information frame is the only thing that really has any relevance in order to update the GUI properly and display the points on the map. So that will be relayed back over UART to the ground station. We have this format here. We're going to tap on and start and end eliminators just so the ground station is able to identify when the message is sent. And you can see, as I said before, we have a checksum that has stayed stable the entire time that this packet has been generated. The ground station will receive the information, and it'll go ahead and update the map to show that information that was gathered. So looking at the latency here for the system, I've got all of the individual communication steps from the ground station to the dongle, all the way down to the ITBD, and then all the way back to the ground station. You can see it's very evident that the 1200 baud is our limiting factor when we look at compared to the 9600 baud that the XPs will be operating at. So in order to send this message from the ground station to the ITBD and back, we're looking at just under a second right here. Keep in mind this 0.9 seconds does not take into account any of the time that it takes the ITBD to gather the sensor data, or that it takes the microcontrollers to actually generate these packets, just the actual time of sending the bits out at these baud rates. Now pass it off to Tim to talk about the GUI software.
Thank you, Aaron. So the overall point of the GUI ground station was, as computer engineers, we could work with just bits coming across the network. But as the fire department, they don't want to sit there and translate which bits are what. So we wanted to make a program that allowed us to display the data in a way that they can understand and easily interpret. This will also check values that come in to make sure that there's nothing ridiculous going on. High heart rates, guy appears in China all of a sudden when he should be in Prescott. It also allows us to transmit a message back to the ADTs to say, hey, watch out, the winds have changed, quickly without having to go over the noisy analog speaking. The overall project was made using Qt, which is a cross-platform environment application. Allows us to program Windows, Android, you name it. This uses mainly C++, but allows QML, which means less programming on my part in terms of making the overall graphics, which is very much appreciated in a short time. Also, we incorporated ArcGIS. ArcGIS is the company that the package that allows Google to display their maps. We are borrowing their developer packet, which allows us to display topographic maps and have the GPS coordinates come in any format we want and translate it into an actual point. So the overall system, we have our start of when the executable is run. It will initialize the window, and then once it is ready, it will allow the user to connect the COM port for data. Then we go into a state of callbacks. Technically, the program is running and would freeze if it was not. But any of these options can be taken at any time the user asks, or if the computer asks. So if the map is clicked, it will grab the cursor location, grab the data package that relates to that GPS location, and display all the data in the widget you will see soon. If UR data is available, it will grab that data, store accordingly. If it's new, it will create a class, or it will create an object that allows us to determine if it's an ADT, an ITBD, and who it's attached to. So it'll say, okay, he came from this ADT, it'll attach itself to that the object of the ADT. If the text button is pressed, it will package that data and send it back over the backchannel UART to the ADT that was recently selected. In terms of time, it will trigger the message at a set rate and change accordingly, depending on emergency mode and whatnot. This is all the autonomous branch. And it will also update the clock at the top so that the user knows what time it is and when the messages are coming in. Here's an example of how the GUI looks at the moment. As you can see, this poor guy is in emergency mode and will need to be contacted to figure out what the heck's up with him. In his case, it's a high heart rate. His battery life is a little down, but he can still be out there for a while. This is in meters. This is all based on a dummy package coming in, so please disregard the topographic data that is in the area. This guy is the ADT in the area. He's designated by a triangle. The ITBDs are circles. Red is emergency, black is non-emergency. And here we'll be switching over to a live demo of the points. So as you can see, we've got all these points moving around. That guy actually just moved. You can tell because the address at the bottom will change to the most recently inputted. This is for general purposes. There's actually 3 points on the map. There's an ITBD that is hanging out next to his commander. All 3 points move from sample packets coming in over our dongle. This is to display just how far we've come. This guy moves the most as he was our original data point. These two have been modified, but they do move and show that, yes, everybody can be moving all at once, and it'll keep track of everyone. This message box right here, I forgot to point out earlier, this is where if any of these points were selected as there's only one ADT in the field, it would send this message to that guy to say, hey, watch out, maybe this guy's in emergency mode. Watch out, there's weather in the area. Hey, your guys have an airdrop coming in. Hey, lunch is on the way. I'm not actually done. As specified earlier, we are saving all of the transmissions that come in. So in this case, this guy is sending to the ADT of this address, the ITBD of this address, and saying, I want to read all the data. This is the transmission coming back saying that he is in a good mode, has good battery life, heart rate is just fine, the temperature is 8 degrees Celsius, and the coordinates of his location. These are also the coordinates that aircraft use, so this coordinate can be grabbed instantly and sent out to aircraft if need be. As you can see right here, I have sent out a message that says test. This was sent from the ground station, and it says that he is going to the ADT of this type, and the packet also has the ITBD that was selected at the moment. Overall, the ground station GUI is fully functional. It stores data in the text file that we have set. It displays ADT, ITBD locations on the map, as we can specify both ADTs and ITBDs. Heart rate, ambient temperature, and emergency mode, altitude, and user ID. This is all information that is being translated back to us. It can transmit and it can receive. So the software on this end is, the bare bones is done. All the little gadgets that we could add on can come later. Overall, the pricing of the system is as follows. This is based on per 100 units. The 245 is for the base ITBD. That's all the components in general. The ADT is just the shield, so you would have to take both of these prices and add them together for the actual ADT component, but as it is, the additional hardware is only $37. The ground station hardware is only the dongle. Qt is a free environment, and ArcGIS, as long as you stay a developer, is free. So that offsets that cost. As a team of 15, that is 15 ITBDs, 1 ADT, and the dongle, that is $4,000, which their shoes are about $3,000. So keeping 15 guys tracked is a pair of boots. In summary, we've gone over the product overview, the general description of what we are doing, the product description in general of this is how we are going to establish our goal in terms of the 3 devices and what they are made up of, our SWOT analysis of our overall project, the hardware and software components of our entire project, the power requirements of how long we can run and what draws the power, the system operational flow and bandwidth, showing the communications between all the devices from each device, the ground station GUI software, the bill of materials, overall pricing, and the summary of our project. Any questions?
I've spent quite a bit of time with you, so we've talked lots. But do you have any advice, since we have a number of students in the classroom who haven't taken capstone yet, for students who will be taking capstone in future semesters? If you knew now what you knew then what you know now, how would you have proceeded differently through the project?
I think one of our biggest problems is biting off more than we could chew. Just set a reasonable goal for your project. Yeah, you have to kill yourself.
It may seem simple from the get-go. We were just thinking, oh, GPS would be too simple, and all that. It ended up being that probably would have been a more generalized system for us. And having all these extra components and bells and whistles just added up to be too much for us to get done and the allotted time we had. Don?
Hey, when you were reading back that data, you said, this is their location, et cetera, and then and I apologize, but I just couldn't see it from here. And you said, yeah, it says their heart rate's just fine. Does it send back like a smiley face or a check mark, or does it send back a numerical value, or is it like?
It sends back a numerical value, and as long as it's not within 200 or above 200 or below 300, it won't transmit that it's also an emergency mode on that same packet. That one will need a translation document afterwards, but the idea is that it's accountability afterwards, being able to tell where they are, what was happening at that time, and the time that the packet came in. It's more of an afterthought, or for the
What's more than a
the text document is more for the evaluation afterwards, how they did, where they were, how can they go about it more effectively. So that's why it would need more of a translation document. In further iterations, we could set it up so that it would say he was perfectly healthy at this point, but maybe he broke his leg, but his heart rate still stayed under what values we thought was fine. It will still show up on here that it was 105 or whatnot, but he may have still been, out of commission at the moment, needed to have the next packet come around for his emergency mode.
I don't know if this better understands too a little bit. The user of this device does not see his own location and does not know his own heart rate.
Yes,
So-
yeah, I get that. I just, he said, and when he was reading it out, he said, this shows that his heart rate's just good, and I was just curious, I can't read from there, I was just curious if it's a number. It's a number. Thank
It's a
you.
number, and eventually there is.
We can program ranges where it won't turn it into emergency mode, and we can change the ranges where it does. And the same thing with any of this temperature, location, all that stuff. So we can program all that based on what the user wants.
This packet, an example, I don't know if you can see it from there. It says that he hit at 201 and 203 here in the mode over on this side, which is a hex value which correlates to a 1 or a 0. It went from a 48 to a 49, so it registered, yes, his heart rate went too high, yes, the emergency mode was triggered. This is why it will still need, at the end, a translation of the text packet coming in.
Oh, so that number is not his heart rate?
The 200 is, but the emergency mode over here, just if he happened to trigger his emergency mode, or the systems along the way caught that and said, hey, this guy needs to get help.
Any other questions?
Within the GUI software, at the bottom of it, you have the data displayed for one of the ITDDs. How is that, like, which one do you know is selected? Because you have the ID, but how does the user from the system know, like, what dot corresponds to what ID?
It's a little hard to see from this projector, but when you click on the dot, it'll outline it with another color. It's just a very faint expanded part to the circle, but it will highlight that dot and say you are selected on this point.
And if there's an emergency mode triggered by one of the units, does the data at the bottom automatically go to that to show that they're in emergency mode, what the temperature is, and things like that, or do you actually have to select a red dot at that point?
At the moment, you would have to select the red dot.
Okay.
Well, it goes from color A to color B.
Yes. Quite a noticeable difference, red and black. But yeah, there are further iterations, and with more time, I would like a display along the side that shows everybody that's in emergency and allow you to click on that to easily find who's in emergency. But at the moment, it was, for time's sake, a better idea to display a larger topographic map and have it be selectable.
Do you anticipate any challenges with the GUI as you go from displaying 3 dots to displaying 48? Or how scalable is your software?
At the moment, it would work perfectly fine to go to 48. I have the software all set up to scan through all the ADTs, and each time it hits an ADT, it then goes through all of its ITDD child objects and displays each one. So if it's empty, it skips over that and goes on to the next one. And the software is generalized so that it displays all the points all the way down, and then it goes back to the beginning. It doesn't say display as it comes in. It rewrites the entire layer. So performance-wise, if I could find a way to not erase every single point at the time the next GPS coordinate comes in, it would probably improve performance. It definitely would improve performance, but as it stands right now, with so few dots, it's easier to just overwrite the entire graphics layer and just replace all the dots.
What's the biggest challenge to a commercial product? What's the next biggest step?
I would say, even though we're using radios to communicate long range, one of the big problems we found when we went to the firefighter academy here on campus was there's a lot of dead zones for radios. So if we could implement radios and satellites,
That was my next one.
that would double cover those two areas. So that would probably be the next step. But obviously, the next step is perfecting this one. So, yeah, something like that.
And I think you guys have done an incredible amount of work for one of the semesters. The project is really impressive. Just want to give you a props on that. That's a huge undertaking. And since I hate writing code, I'm just
Any other questions?
So you used navigation syntax that was being used in aviation or avionics?
Correct. There are a few ways GPS coordinates come in. There's the decimal degrees minutes, decimal degrees, and decimal degrees minutes seconds. We're using decimal degree minutes. I believe I'd have to go back to my software and check it if you don't mind. I will actually do that.
The form that's shown in the text message is the one aviation uses. There's like two different forms.
That would be decimal degree minutes, which I looked through all three different coordinate systems that I was offered on the software, and decimal degree minutes is what was said to be used by aircraft in flight.
So your system, as it is right now, could likely be interpreted with existing avionics?
Not currently. It doesn't have any kind of certifications or anything.
But if the point was given to, say, a helicopter and said, go to that point, they would be able to interpret it.
I think Jim probably better address that. As far as Tim's talking about, if you would have, degrees, dot, minute, decimal, minutes, seconds versus degrees, decimal, minutes. The form that the aviation uses is when they receive the latitude and longitude, they can read out exactly what it is and not have to do a conversion from minutes to seconds. And then the aircraft would know that exact coordinates without having to do any conversion.
And you mentioned the ground station could actually send a text message to the individual units. Is there any indication, like, if the firefighter's out in the field, that he received a text message, so he actually, like, looks at the device? Is there, like, a light or anything like that? I may have missed that.
We currently do not have one. I think it's implementing a sound one.
Okay.
But we hadn't implemented that. Any questions?
Thank you
Thank
all
you.
for your time, and thank you for coming.
Thank
Nice
you.
job.